Welcome everybody to the SEDNOL from today. Our seminar today is going to be given by Hugo Tavares. Hugo is a researcher in the University from Lisbon, and we're very happy that he accepted our invitation to talk to us about free boundary problems with long-range interaction today. Hugo, thank you very much for accepting our invitation, and please, you can start whenever you want.
Okay, so thank you very much. First, antes de empezar, quería decir algunas palabras en español. Agradecer a Mónica y a Alberto por la amable invitación a hablar aquí en este seminario. Espero de vervos en vivo en January. So I hope I will visit you in January. Maybe after the seminar we can talk about this and meet whoever is on the in the room right now. So thank you for coming. So it's a pleasure to speak live from Lisbon, and this is the city, by the way. If you have never visited, please come. And this is about a joint work with. So I'm going to talk about two works. One is joint with Nicola Suave from Milano, Susanna Terracini from Torino, and Alessandro Zilio from Université de Paris. So this is in the old Paris 7, but now they merged some universities, and now he's called Université de Paris. And here are the two papers I'm going to talk about. So one is it's already a 5-year-old paper, and then there is a recent one which is already now. So we finished it last year, and it's now published online. And just what is the seminar about, and what are these two papers about? So basically, this one is just a follow-up of the second one, and there are still many things to do. And okay, let me remove the cameras. And so, in a nutshell, I can say that. So we are going to talk, as the title says, we are going to talk about free boundary problems, and I have to explain a little bit what is this long-range interaction. So, okay, if you don't know what is a free boundary, it's basically, so you certainly know what is a PDE, defining a domain, and when you fix a domain, you fix immediately a boundary. Now, what happens when the boundary is also an unknown of the problem? In these situations, we have what is called a free boundary problem. Free is in such a way that you don't know it a priori, okay? It's an unknown and you want to study about it. And there is a long range or a non-local interaction between different components of the free boundary. So for now, this is a bit vague, and towards the middle of the seminar, hopefully it will be clear why I call this, there's a long range interaction or non-local, in the sense that you will have two sets, let's say, at a certain distance, and if one moves, this influentiates how the other also behaves. Okay. Well, I have the camera on, right? I'm doing some gestures.
Yes, you do.
Just wanted to make sure. Okay. And then what is our problem? So we are going to take a minimum, something from calculus of variations involving densities, or actually the starting point will be something minimizing shapes. Okay. So I'm going to speak more precisely about optimal partition problems, and I have to explain you in the next slide what they are. So partition problems will be the motivation I chose here to bring. Then we can tackle other problems, but this is what I decided to bring here, and they will interact, these shapes, at a certain distance, and this is called long range. Okay, so I will only state precisely the results more or less in 20 minutes. Until then, I will slowly try to build up some motivation so that when I present to you, you find them naturally, hopefully. Okay. So first of all, let me try to explain in 2 minutes what is usually called in the literature an optimal partition problem. So you can say that this is a particular type of shape optimization problem that you might have seen. Optimization problem. So think about the following. So you have, let's say, a fixed omega subset of an Euclidean space, and you take subsets okay, in a certain class, let's say you take all the convex subsets or all the open subsets, you name it, okay? Any class. I'm just explaining in general what it is. And then, well, you take any collection of k subsets in this class, and you have a cost function, okay? A certain function that typically is called the cost function, okay? And a partition for us will simply be a collection of k subsets mutually disjoint. So typically when one thinks about a partition, we think of it as exhausting the whole domain. It's not necessary to put this at the beginning. Typically, it's a consequence of having here an infimum. So you ask yourself, among all possible partitions of your fixed domain omega, if there is one that minimizes your costs. Okay, so it's not hard to think about engineering problems where you want to build something made of several materials and there is some cost, and you want to find what is the optimal percentage of each material that you want to put in your material. Okay, so clearly, with such a generality, like A, it can be whatever. There's no really, not exactly a general theory to tackle everything, as one might expect, right? So what the very, very general results typically are not with sets. You have to relax the notion of solution, not being only sets, but you relax them and asking that your solutions are measures, right? You can go back to the works by Butatsu and Dalmaso and Butatsu and Timo. And then, of course, how people, what they do is then they focus on particular classes of cost functionals where you can really have classical solution here means a set, okay, in your admissible class. And things work out more or less in a better way if you either impose geometric conditions like putting convexity, limiting the number of connected components, or if phi has good monotonicity properties, okay? So a good reference, maybe the best reference if you're interested in seeing a little bit about not only this, but shape optimization in general, this wonderful book by Burkur and Butatsu, Variational Methods in Shape Optimization Problems. Now, one of the examples that have good monotonicity properties, and also because of other applications, is the case of spectral, what are called in the literature, spectral minimal partitions. And this is where you take okay, a subset of Rn, the class of open subsets of a fixed omega, and then you do the following. So you take a partition, okay, omega 1, omega 2, omega 3, omega 4, and you take, for instance, in omega 1, you compute the first Dirichlet eigenvalue. On omega 2, you do the same, omega 3, omega 4, and then, for instance, okay, this is just a toy model, you sum, okay, this is monotone with respect to domain inclusion, and for some convergence, for some set convergences, this is also well behaved. So there are some, this is a typical toy model that also has other applications, and this is the one I'm going to take here today, just for simplification purposes, okay? Now, other applications, because this is really, in some community, a very popular topic, they are related, not exactly for the sum, but for other combinations of lambda ones of omega I, associated to the study of nodal sets of eigenfunctions associated to a higher eigenvalue, okay? Remember that if you have, this is omega, and if k is very large, then you will have, in principle, several nodal domains of your eigenfunction. And in each one, because of the sign, you will get the first eigenfunction, right, in the nodal region. So it's natural that these two, for other cost functions, not the sum, are related. And you can use this kind of optimal partition problems to study, depending on the set, how are the nodal sets of high eigenfunctions. Then they're also related to a special class of elliptic systems with competitive interaction. And with this, I I will just here say more on this later. Okay, I will speak about this later in a more precise way. And also, if you know monotonicity formulas, and I will also point here more on this later, these kind of things also appear to prove some of them, in particular the Alt-Caffarelli-Friedman one that I'm going to state later on, okay? So here is a very incomplete list of names of people that have worked in this problem. By now, I will state this later on, we have a full understanding of this problem, okay? And just as a curiosity, so there are also people like in Lisbon, for instance, working on spectral minimal partitions of metric graphs. And of course, Monica and Alberto also dealt with optimal partitions on manifolds, for instance, okay? So there's a huge literature, and this is just a motivation, okay? So our question now is the following. So this is a typical partition. Now, we wanted that the sets could not be close to one another. Okay, so imagine a structure where you need some space in between these sets. Okay, I will also explain later on. Okay, I keep saying this, but yeah. Why were we drawn into this problem? But basically, what we want is to impose a following condition, that we have a certain R fixed, a distance, and we impose that the distance of the set has to be greater than or equal to some R. So instead of having what I had here before, I will have, maybe this is a set, this is set, this will be like a three partition, and this is a nowhere zone, okay? And this distance is at least R. Okay, and this is what I'm going to consider. And just to be simple, I will focus on this cost function. I will not need to, but I will, just to be simple, and I will put it here, okay? So in the next slide now, I will summarize what is our main problem and what I'm going to talk about here today, okay? So the long range in the title of my talk is this, right? The presence of one set here pushes the other one, not by close range. Close would be, they would be close to one another, but from a certain distance, okay? This is why I call non-local, or better, long-range interaction. So to summarize, this is what I'm going to study, okay? So just notation now. So I'm fixing K will be the number of sets, and R will be the distance, okay, that I impose between the sets. Okay, so I get PR will be, so omega is always fixed, right? And it will be a non-empty set. They are more than mutually disjoint. These sets of the partition, they are at distance at least R. Okay, right. And the minimization problem is as follows. So in each one, I compute its first eigenvalue. And then, for instance, I summarize and I ask myself, is there an optimal partition? And if so, what are its properties? Okay, so before giving the results, working, as you can imagine, working directly with sets should be difficult, right? One, it's much easier to deal with functions. And so we can, and these lambda ones have a very nice variational characterization. So it's very natural as a starting point to write this in terms of functions. Let me try to do it slowly. So we start with, let's say here, a partition in that PR, right? And let me try to write the previous problem in terms of functions. So if I take any partition, I can take the, okay, here I take the first eigenfunction, here the first eigenfunction, here the first eigenfunction. So I get a vector. Let me normalize them. And so it's very natural to, instead of lambda 1, to have here the integral of gradient u to the square. And you have here this constraint. And the fact that the distance between two things, between an omega I and an omega j, is greater than or equal to r, turns into an information about the support of ui. Okay, the distance between the supports are greater than or equal to r. So remember that we are dealing with first eigenfunctions, which are signed. Okay. On each connected component, of course, but you can then flip them, and they can all be. Imagine that they are always non-negative. Okay. So of course, then if I take the infimum among all the functions satisfying this, I get something which is smaller than or equal to my original problem. So this is why I call this a weak formulation. Now, of course, this is a much nicer way of looking at the problem. We wish afterwards to go back to our original one with shapes. What is the challenge? There's a big jump. So let's see what is the jump. So imagine that I have a solution to this set in violet, I think. Okay. And I can always take a minimizer to be non-negative, and it's not hard at all to prove that there is a solution here with direct methods. And now I take the positivity set of each ui. Well, ui is just an H1 function, right? Does the minimality tell me a bit more? If it tells me that the omega i's are open, then it's not hard to show the other inequality. And so my plan is to start by studying this formulation, then to prove that everything is open. For instance, if the ui's are continuous, I'm done. And then I have a way of going back to my older problem. But this is a big jump, what I'm stating here. Okay, and so what are my results? Still not in mathematical terms. We prove the existence of solution of both problems, because afterwards they are equivalent. Okay, you can really say that the functions are continuous, so those sets, the positivity set, the nodal regions are open, and so you have a solution to your original problem. We can also relate these with an elliptic system, this time with a non-local competition term, and I will be precise in 10 minutes. And then things become even more interesting, right? So now I have a solution. I just know that there are open sets. Can I say more about these sets? So so the free boundary, by the way, of the title is, in this picture, these three lines here are the boundaries of these, okay? And this is what you want to know. Are they regular? Do they satisfy some condition because of this distance to be less than or greater than or equal to r? Does this impose something? How about the eigenfunctions? How regular are they? Of course, inside the domains, they are C infinity by elliptic regularity, but I don't know a priori how is the boundary of the optimal partition. So what is the regularity of the eigenfunctions up to the boundary, right? Then something that is called in the free boundary world, the free boundary condition on the regular part of the free boundary. So let me do the picture once again. What is a free boundary condition? So imagine that this is omega 1, a set, an optimal set. This is another set of the partition, and this is another set of the partition. In each one, I have a first eigenfunction, u1, u2, u3. Right. So they are all 0 here. Everything is 0 in this nowhere zone. They are 0 here, but the normal derivative will not be 0 here by Oph's lemma. Is there any relation between this function and this function, or maybe between the way this function arrives here? So what is the derivative of the function here with respect to something at distance r, let's say, on the other one? This will be a free boundary condition. So a condition on the free boundary, which is made of these three lines in this picture. And then finally, and this is the last paper, the second of the two papers I mentioned, To study. So I have two problems, right? The long range that I keep drawing because of the pauses. I do it on purpose, okay, on Beamer. And then this is the long range problem with distance r. And I have, let's call it the short range, which is the original one that I started to talk about, where you just ask that they are mutually disjoint, right? Now, what happens when, a natural question is, what happens when r goes to 0? What kind of convergence can you show from here to here? Okay, and yes, we can. This is the content of the second paper. Okay, so before I state all of this in mathematical terms, I think, okay, first I will do a plan of the talk, and I will start by reviewing the local case, which is where you don't have a distance between the sets, where as I told you, we know basically everything about optimal solutions, okay? And with this, I will show you what we can prove, what are the differences for our problem with the distance, and what is still open. And I will also try to explain why the second one is much, much harder than the first one. Okay, and this is why, well, some results are different and some we have no idea yet how to tackle. Okay, then I will give you just a flavor of some of the techniques used in the proofs of some things. I will definitely, this is just a slide, so I will leave some open problems, and time permitting, I don't think so. I have some other examples here. Okay, so because I will spend the seminar just mentioning the sum of lambda ones, but this is just an example. Okay, so I could tell the general case. Right. Okay. If you have any question, please don't just open the microphone. Okay. If you want to review some notation, just ask. Right. Okay. So let me now do a quick literature review of the local short range interaction. Okay, where you don't have distance. Right. So what I'm going to talk is the combination of several papers, and I'm going to resume everything in a single slide. But before, I keep repeating the definition so that you don't get lost. Okay, so this is a partition. We just ask the sets to be disjoint, and I want to minimize this cost function. I compute lambda 1, lambda 1, lambda 1, lambda 1, and I ask myself, what is the partition that minimizes this sum? Okay, this is the weak formulation. Okay, where instead of sets, I deal with functions. So I normalize them in L2. So this is quite natural to become this. And the fact that they are disjoint is translated into there cannot be two non-zero densities at the same point. So at each point X, or at almost every point X, ui times uj is 0 for every I different from j. So this is the replacement. So as I said, this in general is less than or equal than the thing above. Okay, so these are some references, right? Some names, actually. I'm not giving the references. And, well, if you combine 4 papers, okay, starting with Caffarelli and Lin, Conti Terracini Verzin, then myself with Susanna Terracini, then a recent one by Onur Alper, you have the following. So first of all, the problem has a solution. You have functions, and the sets will be the positivity sets of each component, and they are Lipschitz continuums. And I'm saying here that this is the optimal regularity. Why? Because U1 will be an eigenfunction in its positivity set. Eigenfunction, so outside is 0. So if this is regular by Hopf's lemma, the gradient arrives here in a non-zero way, while here it's 0. So there is a discontinuity in the gradient. So this is why I'm saying that this is optimal regularity. Of course, there is something better than Lipschitz, but let me say that Lipschitz is optimal, okay? Right, now the second question is, what do we know? So this is the thing, the good thing about the densities. What do we know about the optimal sets? Okay, imagine that this is an optimal partition of the short range case, okay? Then look at the picture before looking at what is written above. It's made of regular parts and these points. But they are just points, right? There are not many in this case, triple points. There could be points with a higher multiplicity, but apart from these points, the free boundary is just a collection of regular lines, right? And in general, this is the picture. So let's call the free boundary the set where everything is 0. And this has dimension at most n-1. Actually, it's n-1. And you can split it in two parts. So in blue, it's the regular part. So it's a union of regular hypersurfaces. Look at the picture here. And outside, it's what is fixed, the omega. And you have a free boundary condition. So I mentioned a free boundary condition before. Let me explain what it is again. So look at omega 1, you will have an eigenfunction u1. And on omega 2, you will have a first eigenfunction, call it u2. u1 is just an eigenfunction in this set, and it's 0 everywhere. u2 is an eigenfunction in this set, and it's 0 everywhere. They both arrive at the common boundary being 0. So let's look at the first derivative. Now, since this is regular, the derivative only has a normal part, right? Because the tangential part is 0, because here the function is 0. Now the normal derivative matches on both sides. So this is what's called the free boundary condition. It's how they communicate through the free boundary. This, you can prove that this is different from 0. And I will mention this as being a reflection law. So imagine that your profile is one-dimensional. Okay, and let me draw. So imagine that this is a point here, and you are looking at the values of the function u1. This is the graph of u1. And imagine that this is the graph of u2. This looks like a cusp, but it shouldn't be, right? What I'm saying, what this condition is saying, that they arrive with the same angle. So let's call this a reflection law. And this will be, let me already anticipate, quite different when we have things at a certain distance. The geometry of the boundaries will play a role. Here, they just match. What remains is just small. Okay, I don't know if everyone knows these terms, but okay. The Hausdorff dimension is at most n-2. It actually has a finite hn-2 measure. And it's also, for those of you who know, it's n-2 rectifiable. And you can also prove what is called some stratification results. So for people in free boundary problems, probably you know what is a stratification result. And this is, by the way, content of this last paper. Okay, so I'm almost finishing in this introduction about the short range case. I said before that I would mention a connection with elliptic systems, okay? And this connection is actually how many of these things are proved. And the idea is the following. So this is the problem I want to solve. And this is the difficult part. Okay, this is very singular. So the idea is to, instead of this, perturb this problem by something that penalizes the fact that two densities live in the same place. And this can be done, for instance, you can take like the product of any two functions here, but then the absolute value is not differentiable. So let's take the square, for instance. And I penalize. So I put a very, very large constant here. And it's reasonable. So this is penalizing. If this is non-zero, I want to minimize this. It's not good that this term exists, right? So it's very natural, hopefully, that if this constant here is very, very large, at the limit, it's better in terms of energy minimization to have this. Okay, so it's exactly what one does, right? So to remove this constraint, one perturbs the energy and removes this thing from the set, and we minimize it here. This is quite easy, right? It's just direct methods of calculus of variations, and just want to see there's a linear, there's a non-linear system, a semi-linear elliptic system associated with this, which consists of, in black, just a bunch of single equations that are kind of eigenvalue equations, right? And then they are coupled through this red term. Beta will be very large. In the equation, it appears something which is negative. And so this is like a competing term. Okay? And when beta goes to plus infinity, these solutions converge to the solutions of the other problem. Okay, and this is how actually one proves many of those things. Okay, so ideas about the proofs, or
Hugo, can I ask you a question?
Sure.
In this part, you propose this weight, like with this squared, but if you had put to the 4 or to the 6, you always get to the same limit, or
Yeah. Doesn't matter.
Doesn't matter. You always get to the same thing.
No. Doesn't matter the power. I mean, you just need this to be C1. So
Okay.
it doesn't matter. Yeah. That's it. You always get the same. So ideas about the proofs, or why is the long range problem difficult? So I'm going to explain the techniques in 2 slides that are used just to convince you that then in our problem, the long range problem, we cannot use any of that. Okay. So very briefly, to prove regularity of solution of the boundaries, one typically want to study what happens close to a point. To study things close to a point is doing a blow up. So it's to look do a zoom in. And if things are regular, what you find out is a hyperplane, right? The challenge then is how to go back. But you study these functions, this blow up. So you take an x naught, you want to look close to it. You take an epsilon very small, and then depending on what you want to do, you normalize it, because there's a risk that you find 0 at the limit. So rho n is typically some normalization, and this is just the zoom. Okay, you do a blow up. Then to prove many things, you prove many things by contradiction. You want to exclude some cases. You have Liouville type results. These are non-existence results. The most famous one is a harmonic function which is bounded from below should be constant. Okay, this is an example of a Liouville type result, and you get several Liouville type results appearing because you want to study what you can get at the limits of this blow up, and you want to exclude some possibilities. And then monotonicity formulas. Okay, they are basically the following. So there is actually, I don't think, the general definition of what is a monotonicity formula, but in this context, they are typically the following. So you want to study, again, what happens close to a point. You take, for instance, a ball of radius r, and you define in a smart way a certain quantity that you find out to be monotone. And this gives you a lot of information about the local behavior of your solutions close to a point. Let me give you the example that I will need later on. So this is the Alt-Caffarelli-Friedman's monotonicity formula. Look at the picture, and then slowly I will point upstairs. Okay, so you have 2 functions which are non-negative, and they are segregated. So you cannot find let's say if these are densities, they cannot live at the same point. So let's say that this is from this line above is where U is positive. Let's say that from this line below, this is positive. And this is the common zero set. Now, you have a harmonic function where U is positive and a harmonic function where V is positive. Okay. And they actually don't communicate, right? I mean, there's no compatibility condition, just the fact that this is a common, this is the area where both are zero. And okay, they extend by zero to the other side in a continuous fashion, and the energies are locally, the H1 norm is locally finite. How can you glue these functions? Are this gluing arbitrary? The answer is no. So if you take a point x naught here, and you take a ball here of radius r, this product, that I will explain what it means. There's a product that only depends on r. This is a function of r, is monotone. What is this saying, morally speaking? So if instead of x minus x0, you get r here, what you get is an average of, so you can think about this as an average of gradient of u squared. It's not exactly an average. Why is there 1 over x minus x0 to the n minus 2? Because it's the fundamental solution. So it's better, instead of taking the average, to take this quantity. But morally speaking, you have kind of an average. Here, the same. So this is saying that the average of the gradients of one function and of the other, the product is monotone. So for instance, this is bounded. So if one is going to 0, then the other should explode. So there's a balance. There's a limit when r goes to 0. So this is really a strong statement and gives a lot of information about the functions u and v. Not individually, but if you know how one behaves, then you have a lot of control on what you can put on the other side. Just as a fun fact, the way to prove it involves an optimal partition problem, like the one I'm mentioning here. The proof is just compute the derivative in R. When you compute the derivative in R, this ball becomes a sphere. And look at here what happens. This sphere induces a partition in two parts, right? So the fact that this is increasing or non-decreasing is equivalent, if you look at the proof, to something like this. I will cheat a little bit just to simplify, but the proof is equivalent to show that an optimal partition problem on a sphere of radius 1 of the sum is greater than or equal to 2, where this 2 is this 2 here, okay? Actually, this is just the case in dimension 2. In dimension 3 or higher, it's not exactly the sum, it's a different combination, but at the end of the day, this is equivalent to a free boundary point. Okay, I will need this later on. Okay, so
in dimension 2, do you add some logarithmic correction to the fundamental solution, or is the
no,
same?
no, no, yeah, this is the natural question, but no, you just, it's easier. You don't need this at all.
Okay.
Yeah, yeah, this is the natural question. Thank you very much. Right. In this case, it's really an average. So actually the proof, you start doing the proof in dimension 2, and then it's by induction in the dimension. This is one way to do it. Yeah, because in dimension 2, it's much easier. So you just need the fundamental solution in higher dimensions. Thank you.
Thank you.
Okay, hopefully I didn't digress too much. Yeah, I think I did. But in any case, let me now finally state my results. Okay, in the long range interaction. So now the statements. Okay, so back to the basics. So we were dealing with this problem. So I have a fixed omega. I have here, for instance, a partition in 3 sets, and the distance is r. Okay, I recall that this is the weak formulation. Okay, in terms of densities, I'm minimizing the sum of the H10 norms to the square with normalized in L2, and this becomes this condition here. Now, what the first part is equal in the short and long range. So first of all, as expected, right? Otherwise, I would not be mentioning this problem. We have a solution, okay, of the one below. We start by having a solution of the one below, and then we prove optimal regularity. And how do we do all of this? Well, we relate this with a system. Now, the previous system had a local interaction. It was something, it was related to Alberto's question. It was something like this, J to the square. And this was at the same point, right? Because you just wanted to penalize the presence of 2 at the same point. Now you want the presence of 1 at one point to penalize what happens in a whole neighborhood. So you need something like this. You take a potential supported in a ball of radius r. And well, and now the presence of this one penalizes the presence of all the others in the whole neighborhood of radius r to the point. So you can take here any v, it doesn't matter. So you can take the characteristic function if you want. You can write this in terms of a convolution. And the local case is when you take v equal to the Dirac delta, where you recover minus beta ui uj squared. Okay, so this is the non-local system. Actually, this was the original motivation for us to consider these problems. There were some problems in physics where the interaction is of this term. Because it's quite natural that if you have particles interacting and repelling each other, it's more reasonable that the fact that the presence of one particle influentiates what happens in a neighborhood of a particle, not just at that point. So actually, this is the original motivation for us. Okay, then we get, now take any non-negative minimizer, okay, doesn't need to come from a system. You have optimal regularity. Remember that optimal regularity meant Lipschitz, okay, because of Opf lemma. So the UIs are Lipschitz continuous. In each positivity set, you really have a first eigenvalue, an eigenfunction. And of course, if you extend in the whole domain, you just have a subsolution. Okay, so in particular, what this slide is saying is that I can go back to my problem with shapes, because if it's Lipschitz continuous, then the UI is continuous, right? And so this set is open, and so you can prove the equivalence between the two formulations. Now, up to now, nothing much different. So the fun starts now. So what is different if we consider this interaction from a certain distance, right? What changes? Well, so remember that the distance is at least r between sets. Now, the simple fact that we have this constraint imposes that at each point, we don't know regularity, but each UI satisfies an R, where R is the one that I put in the domain of my constraints, an R uniform exterior sphere condition in omega. Moreover, clearly in the problem I put distance greater than or equal to R. For minimizers, given a set of the partition, there will be one by minimality at distance exactly R. And in fact, this one of the possible exterior balls will be centered in another set of the partition. Okay, so this is the content of all this same. We cannot, what is one of the biggest open problems here, we don't know how to do the regularity part. Why? Simple as this. I've mentioned everything that I mentioned before was local. Blow-up arguments, monotonicity formulas for small radius. If I do a blow-up here, I lose all the information here. So all those techniques cannot apply, at least directly, to this problem. So we don't know yet what to do. Maybe we need to choose and do two blow-ups, but a priori we don't know anything about these sets. It's a free boundary. So the best we can do, well, the best we could do was to prove that the boundary had zero measure using the fact that it has an exterior sphere condition. but actually this can be improved by a very general result in a paper by Caffarelli, Patrizia, and Kitalo that says the following. So maybe in the future you might need this. If you take any closed, it's very general, bounded set in Rn, and you take the set at distance, let's say 1 or whatever, then this has a finite perimeter. Basically, what they do is they look at the distance function. They are a sub-solution in the viscosity sense of a certain problem, and then they do some computations that can prove that the perimeter is finite. So actually, the best we can say is that the perimeter is finite. Then, what is the free boundary condition? This is my favorite part, I must confess. So remember that in the local case, let's say like this, you have U1, U2 here, omega 1, omega 2. The derivatives would arrive exactly the same. So the normal derivative on one side would be equal, there's the reflection law to the other side. Now the question is, if they interact at a certain distance, can I say something? So if this is the set which is closed, so if this is precisely R, do the normal derivatives have a relation? The answer is yes. But we have to assume regularity, okay, which we cannot prove yet, but we suspect that parts of it are. So assuming that we have regularities, and this is to speak about curvature, and assuming that the principal curvatures, so since we have an exterior sphere of radius r, the principal curvatures are at most 1 over r. We need to assume that they are far away from 1 over r. I will have a picture explaining why. But under these conditions, this is the free boundary condition. So in the local case, where they are glued, the two sets, this is always 1. This is equal to this one. In general, when they are far apart, the curvatures play a role. Okay, so in the flat case, it's 1, as it used to be, but in general, you have the product of the ratio of the principal curvatures and on one side and on the other. There may be a nicer way to see this is that you can, everything, we are assuming regularity, right? So you can prove that this is equal to 1 minus r curvatures of x naught. And so you really see that when r goes to 0, you recover the previous result. So the curvatures play a role. Okay, so delicate step. Why do we need, what could go wrong? A lot of things. So we need to avoid this case that the principal curvatures are exactly 1 over r, because at this simple example, which I tried to draw in the best way I could here. So let's consider the domain, which is the following. It's a straight line and then half of a ball of radius r. Let's compute the set at distance r from this one in blue. Now here, this is r, straight line. Now here you have an arc. This is part of a sphere of radius r. The same here. So, you have here something which is super regular, and on the other side you have a cusp. So this is also another reason why the free boundary theory is probably super hard, because you have to exclude these kind of things. But a priori, how can this could happen, right? Okay. Okay, so finally, our last result concerns the case of connecting the non-local case, the long-range case, where you have a distance, to the one about which we know everything. Okay, when r goes to 0, do we in some sense can relate these two problems? And the answer is yes. And this is the content of the second paper. So just to remember, CR was the energy associated to this side. The optimal regularity was Lipschitz, and we can prove uniform optimal bounds when R goes to 0. Okay, so this is the content of the paper, right? So this optimal bounds. And so as a simple corollary, actually we can show a precise relation between the two levels. Okay, one is the other plus a no of R. So the levels converge, the energies converge. And so if you take a solution of eigenvalues of the non-local case, at the limit, you get a solution of the local case. Okay. So my time is out. Actually, I spoke too much. Alberto, please help me.
You can still have like 5 minutes and then we
Yeah. So I will ask you. So I have 5 minutes, so I will let you choose. Okay. So let me tell you. So the first time I spoke about this, I could do everything, but I think every time I repeat this, I talk more and more. And so I have less time at the end. So I have 3 things that I can tell you, and each one takes 3 or 4 minutes. So I will let you choose maybe what you would like to know. One is the free boundary condition, the one that involves the curvatures, where it comes from. Condition. How we prove the Lipschitz continuity for R fixed, or the uniform. So I have time for one. Uniform Lipschitz continuity as R goes to 0. So let's do a short poll maybe. What would you like to?
I would vote for the free boundary condition. So if everybody else wants to quickly vote, just activate your microphone and say so.
Okay, I will do that. Okay. Yeah, it's the simplest one. I bet it is. Yeah. Sorry about the bad time planning, but I got a bit. Okay, so free boundary conditions and then open problems. Okay, so right. So the question is the following. Okay. So what do I want to show you is basically where is this formula coming from, right? So let's see if everyone understands what I'm going to talk about. So the situation is as follows. We have, let's just take the case of 2 densities. We have 2 densities that minimize a certain problem, okay? Minimize the sum of L1 square plus U2 square. So we have infimum with L2 norms equal to 1. The distance between the supports is greater than or equal to R. And yeah, I think that's it. And we assume regularity. Okay, and we want to show that if I take a point X not here, in the set, in the boundary of the set where U1 is positive, and I take the point at distance R, let me call it Y naught, then the normal derivative to the square divided by the normal derivative here to the square as this expression. Okay. In the local case, they match. Okay, so we have a problem of which is a minimum, right? It's variational. So what we do is we build a variation with a certain parameter and use the minimality. Let me be more precise. So I need to perturb this. Okay. Remember the calculus of variations. How do you deduce the Euler-Lagrange equations? You do a variation, right? You put plus epsilon phi. Here, I want to deform the sets, not just the functions. But I have this. This is the hard part. Right? And this is why, in general, when you don't have regularity, what kind of variation can you possibly do keeping this if you don't know anything about it? But assume regularity. So what you do is the following. So take an X naught here, and let's assume that there is a piece of this boundary that is regular. So let me take here a ball of radius R. So, and let me call gamma 1 R this part in black, and assume it's regular. Okay, it's a part of the free boundary that is regular. Right, I need to do this locally, so I fix a cutoff function supported in this ball. Okay, and now I want to, for instance, push this set outwards. Okay, I want to do this tiny bit. What can I use? Well, I can use the normal. So let me introduce a family of deformations from Rn to Rn that do the following. Outside of that ball, they don't do anything. I want to do this locally. Right? If a point is in that boundary, I push it outwards using the normal, the exterior normal. Okay. How? Well, I do this. Now I want to keep smoothness. So this is why I have the cutoff function. And I want to do a perturbation in epsilon. Okay. And then I just extend this in a C infinity fashion. So this set in blue becomes a little bit larger, like this. For each epsilon, I have a new set. And in this new set, I can take the first eigenfunction. Okay. Now I want to, I can normalize, but I need to keep this. So if this one I pushed outwards, I need to push this inwards and remove this part. Well, since I'm assuming regularity and if epsilon is small, in practice, I can really write everything explicitly. I use the normal derivative here, the unitary normal, multiplied by r. I forgot an r here, sorry, because this is at distance r. And I push this inwards. And so I have, and then I take u2 epsilon, the first eigenvalue of this smaller set. Okay, this is an admissible a pair for this. And I can do the derivative in epsilon is 0 because it's an infinite. And basically what happens is that, so in general, I'm just perturbing these two, right? I have these formulas from shape optimization that tell me exactly when I perturb a domain, what happens to the first eigenvalue, which is basically this term. And they just depend on what happens, okay, depend on the normal derivative to the square and on the boundary. Why are the signs like this? Well, lambda 1, you made the set larger. So if the set is larger, lambda 1 decays. So this explains the minus sign. The other is perturbed inwards, so the set decreases, so the derivative is positive. Now I plug this here, I have a minimizer. This is for any test function, so I get an inequality for any test function. And since this is for any test function, I get this inequality without test functions by making things converge to a characteristic function. And gamma 1 and gamma 2 are just, this was the regular part, and then use the normal, and you see what is on the other side. Now, of course, I did it in such a way that I was pushing one inwards and the other one outwards. I can do the other way around. Push this one inwards, this one outwards, and I get the opposite inequality. So in conclusion, I have these two sets at distance r, and I can relate the integral of the normal derivative with the integral of a normal derivative here. Now I normalize, I divide one by the other and normalize. And now I pass to the limit when this ball is going to the point. So this one, if everything is smooth, converges to this ratio. And this is a nice exercise if you are teaching one of these courses, differential geometry or something. It's just a change of variables, that because this set is this one plus the normals. And normals are related to so the derivative of normals are related to the curvatures. And so you can prove that when r goes to 0, you get this. Okay, so just to thank. These are the open problems, right? That we don't know what to do. The regularity problem for r fixed, the convergence of the free boundaries as r goes to 0, and the inverse problem. Can we, from a solution of the short range, construct a solution of the long range? We don't know what to do in any of these three situations. And so, thank you very much.
Thank you
Sorry.
very much,
Sorry.
Hugo. Please, and I will
Yeah,
ask
sorry, taking
the
1
people
hour.
in the room to open their microphone and just thank Hugo.
I have a small question only. Is there anything known about, can you hear me properly?
The what, sorry?
Yes. Go ahead. Go ahead. We
No,
hear you.
is there anything known about the number of solutions for this on the regularity assumptions or on the?
No. The number,
No.
no.
Not
What
at
we
all.
know, yeah, what we know of the short range is that they are unique up to, or you can always add something of lower dimension. So the uniqueness is always up to doing something, right? Or if you are in a ball, you can always rotate. So in the short range, yes, we have this kind of results. Uniqueness up to, so in a certain class of equivalence, you have uniqueness. Yeah, in general, no, we don't know. Thank you.
Thank you.
Are there any other questions? I have a question. You in all your talk, you always wrote a bounded domain, no? Something like a strange ball, but probably can you do this also in unbounded domains?
Sure. I mean, why not? Maybe putting a potential or something, but
Or a
I mean,
nonlinear
it depends
solutions of a
on the question.
nonlinear
Like,
problem.
Lipschitz continuity is local, so yeah, sure. The existence part is the only thing that is different. But the existence is the least complicated, at least from the, it's just direct methods in this case. So
because in unbounded domain, probably this last question that you wrote, that if you start from a local problem, can you go to the long range interaction? Maybe it's easier, no? Because you have a lot of space to just move your partition.
yeah, I don't know. But yeah, what do you, I mean, you could do?
I mean, if you have, for example, only two components, you just separate them. If you have three,
no,
you
but
can
it's
also
not that,
just separate them.
Yeah, but it's not that simple, even in a ball. Why is that optimal? I mean, it depends,
I don't
right?
know.
It depends, I mean, it depends on the problem, because you cannot do lambda ones, maybe you have to put a potential. What are the assumptions on the potential?
In simple domains, have you, or is it possible to do a numerical approximation of these partitions?
Yeah,
Have you tried,
we are looking for
anybody
someone.
has tried?
If you want, please go ahead. None of us can do it.
Well, Alessandro is very good with that, but has he tried?
No, Alessandro did some things in balls. Yeah, where you get symmetry. Sure. Alessandro, yes. Okay. But we didn't explore a lot these kind of things. I mean, what is expected from what we could see, but in very specific cases, is that the same result of regularity holds, right? Apart from, so you could have like triple points now are harder because you could have things like this. Whoops, but this is not allowed because everything needs to be always at distance r. So maybe something like this. So these points. So this is what it probably will look like. Actually, when we're working hard on this, one of the approaches that we tried, because okay, yeah, you have this and you don't know what's in the other side. We tried to study the curves, let's say at distance r/2, and seeing if we could apply a local theory to those, but we couldn't do it. But this is the general picture we have in mind that should happen probably. So if a local case is always like this, maybe you have something of dimension 4, something like this, then probably, at least for R small, you will have maybe this. Set is here, maybe set it here, set it here. Yeah, something like this, right? Whoops, okay. You get the point, right?
Yeah.
Probably. but oof.
If you impose some symmetries on your domain, like in a ball, can you prove any of your assumption on regularity, or not even in this case?
I mean, if it's probably you can. Like what?
I don't know if you have some particular cases where this assumption that you imposed in the general setting could be verified.
Yeah, I mean, yeah, if you have symmetries, then probably you immediately exclude the case of the cusp, which was something like this.
Mm-hmm.
And I'm sure it's easier. Yeah, I'm sure it's easier.
Are there any other questions?
We didn't try. Thank you.
I have a question. You mentioned at the beginning of your talk that sometimes people use, instead of sets, measures.
Yes.
So what are the conditions that you ask in the measures, and do you still do like this convergence of functions, or it's more convergence of measures?
Measures,
like,
yes. So what is the condition on the measure? Oh, well, since I'm online, I can cheat a little bit. Let me advertise this a little bit. Just let me see if it's easy to find. Measures, or I can go directly to the paper. Sorry, but that's about mine. If I have it here, yeah. Let me just see if I can find it. I don't remember, honestly. But then, okay, you would go back if the measure was.
I mean, I am wondering if you have the same like space of functions, similar space of functions, but then you are just weighting your functions or like integrating with respect to this measure.
No. These are very general, so very weak results, in the sense that they define a relaxed formulation of this minimization problem in terms of measure. And then they can prove in this class using confidence of measures, and that's it, that there are optimal measures.
Okay.
And nothing more than that. So they cannot go back to sets. So this was just to motivate the thing. Okay, it's completely different. Yeah, it's a relaxed formulation that then they cannot go back to the set.
Okay,
Hugo, I have a question. I cannot use my video, it doesn't work, but do you suspect that, for instance, that you can get, excluding some bad behavior, that maybe you can get easier results, say in dimension 2 or something like that, and that then you could use some symmetries to extend to higher dimensions or something?
So even in dimension 2, without anything else, we cannot do it.
No, but you have to exclude. I mean, in dimension 2, maybe it is clear what is the bad behavior. So what are the bad things that you have to exclude?
The cusps are the cusps.
And the cusps.
Precisely these arcs of circumference that give rise to cusps. Yeah. You can have angles. There's nothing wrong with angles. So I didn't mention, but so I should probably, about this kind of things, there are only 2 papers that I know. So, but mainly one, which is this one that inspired us a lot. It's related and not related, let's say. We were working at the same time. Their point of view is more from systems and the non-variational. So they mainly work with p equal to 1 here.
Okay.
And you can write this as an integral, okay, of x and uj. And there, in fact, in dimension 2, they can do a little bit more, but only in very, very specific. Suppose that you have a graph and you already know that you're on the other side, it's also a graph, and they have in dimension 2 a result saying that if you have like a triple point, then these angles should be the same. They can exclude that limits of this, but they use the fact that they use the dimension 2, dimension 2, and the fact that we are coming from a system and p equal to 1. And when p equal to 1, just believe me that things are very different. We can have extra inequalities coming from the system that are not true in dimension for p equal to 2, for instance. And they can show that for triple points, these angles are the same. They can exclude cusps in dimension 2, regularity just in some cases, but yeah, progress has not been very satisfactory in this.
Okay, thanks.
Thank you.
Any other question?
Maybe there's
Well,
one.
if that's not the case, then let us thank Hugo.
Thank you.
Thank you very much, Hugo.
Thank you very much, Hugo.
Hope to see you soon.
I hope to see
Me
you
too.
soon. Yes, yes.
We're waiting for you.
Yeah, maybe we can stay a little longer just discussing the dates. I have more or less the idea, maybe in January. I think we can maybe fix the dates if you wish, if we stay a bit now after
Yes,
the
yes.
No, January would be great.
Okay, okay.
Okay.
So goodbye. Hope to
Thank
meet
you
in
for the
person.
talk.
For everyone.
Wow.
Very nice talk, Hugo. Very nice and very clear. Thank you very much.
Sorry that I spoke so much. I think I got too excited.
No, but it was beautiful. I enjoyed it very much.
The
As I
hour
said,
passed by
every time
very
I
quickly
speak,
for
I add
everybody.
more things and then
About this last convergence result that you showed, Hugo, it means I think it appears some Hölder norm there, right?
No, it's Lipschitz.
So, it's Lipschitz. So does this mean that there is a Lipschitz deformation from one set to the other? If I wanted to see the convergence in sets,
no, in sets, I don't know.
A...
Yeah, this is one of the open questions. Yeah, it's just for functions, for the eigenfunctions.
So it is not clear what it means for sets.
No. I mean, we don't know anything about the sets apart from being, okay, they satisfy an exterior sphere condition. They are open. The boundary has finite perimeter.
So is it clear that the Lipschitz convergence of the functions does not imply a Lipschitz deformation from one to the other?
What is a probably a Hausdorff convergence? Yes, but I don't know.
Okay.
Okay. So Monica and Alberto. Let me just
See you.
see you. Gracias.
Thank you very much, Hugo.
So you're saying after the 6th, right, Alberto? I mean, I think we can speak. You wrote me an email saying after the 6th.
Between the
so for you, it's the same. 6th of January.
Yeah, for me after the 6th is okay. At
So
the
I think I would
at the
really...
end of January, I have to go to Brazil. Let me see when. I don't remember.
So I was planning to come, yeah, exactly. Maybe 6 or 7, and then stay the whole week until the next weekend. Would be okay.
That's perfect with me. Yeah.
Okay. So could you give a help with the local like a hotel and local thing?
Oh, sure, we do everything.
I can take care of the trip if you want.
We take care of everything.
And
are you coming alone or are you coming with the family?
No, alone.
So how are your children doing?
They're about coming alone. I'm now reading this novel. A colleague of mine that just arrived recommended me this novel by David Lodge. I don't know if you know. It's a trilogy called the Campus Trilogy. And the first part is about so it's a novel about university professor conferences. It's very nice.